So some students find it helpful for us to kind of just lay out all of those different kind of forces that we were talking about throughout all of those different videos. So I wanted to lay them out for you like this. That way, if you want to use this as a way to compare all of your different things together. I like to start at the strongest end here. We know that out of all of the different forces that we talked about, that the ionic force is the strongest of them all. And that is the force that we would see between a positive ion and a negative ion, right? Because ionic compounds have a metal and a non-metal. So ionic is going to be the strongest thing. So when you're trying to compare everything, first decide if something is ionic or if it's covalent. Because if it's an ionic, you know it's going to be strong. There are two ways that we could compare ionic compounds. We said that if they were smaller, a smaller size, or if they had a greater charge difference, that they were going to be stronger ionic bonds. Okay? The next strongest force that we talked about were those metallic bonds. And metallic bonds obviously are going to be found in samples of metals. Okay, it doesn't have to be a pure metal. It could be a combination, a mixture of metals, if you will. But metallic bonds are those metal samples. Our key word here is delocalized. Because remember, the electrons are going to be floating in this little sea of electrons between those positive nuclei of the metals. We did say that the more valence electrons that we have means that we have a stronger metallic bond. Okay? Now, we had three different types of intramolecular forces that we talked about. We talked about ionic, we talked about metallic, but what was that first intramolecular force that we talked about? We talked about the covalent. And the covalent out of those three is the weakest. But there are three different types of covalent intermolecular forces at play here. And so if you have something that is covalent, you have to figure out which one of these three it would fall in to determine its relative strength. So the strongest covalent IMF force was the hydrogen bond. So remember, this is a strong dipole-dipole interaction that occurs when hydrogen bonds to nitrogen, oxygen, or fluorine. So for example, if you have water, which looks like this, we've got our negative dipoles and our positive dipoles. The hydrogen has to be bonded to the oxygen in order to get these dipoles. All right? But this right here is not our hydrogen bond. That's not our hydrogen bond. That's our polar covalent bond. We have to draw a second water molecule so that we can show this attractive force here. That is our hydrogen bond. Okay? Our next strongest intermolecular force in covalent molecules was those dipole-dipole interactions. Now, with dipole-dipole interactions, those are found between polar molecules. And how do we know if something is polar? It has lone pairs, or it has different ends. So again, if you're trying to determine if something is polar or nonpolar, you're going to have to draw the molecule so you can actually see what that looks like. So a polar molecule is going to have lone pairs, or it's going to have different ends. So if you were to draw that, I'm going to draw something very similar here to the hydrogen bond, but I'm just going to substitute fluorine instead of the hydrogen. We still have dipoles because of that electronegativity. Oops. Got involved with my water here. Those are fluorines. We still have dipoles because there is an electronegativity difference between oxygen and fluorine. This again, that's a polar covalent bond. That's not my dipole-dipole interaction. I have to have this attractive force that is my dipole-dipole existing between those two molecules there, the partially negative end of one and the partially positive end of the other. The weakest force of everything is going to be our London dispersion forces, or our LDFs. So we know that London dispersion forces are going to be found in nonpolar molecules. Now, remember, we're looking at molecular polarity here, not bond polarity, in order to determine which IMF is involved. It's molecular polarity. So nonpolar molecules, remember, they're going to have the same ends or no lone pairs. So for something like methane, which looks like this, same ends all the way around. This is not our LDF because that is a nonpolar bond. We would have to draw another methane molecule, and the attractive force that exists between those is the LDF. Now remember, these are just temporary dipoles. That's why it's the weakest, because it's just temporary. We did say that there were ways to compare LDFs. We said that if something was more polarizable, and we know if it's more polarizable because it has more electrons, so you can look at electron cloud, you can look at the number of electrons in there, you can even look at the mass. All of those would help you to determine about the number of electrons. It's going to have a stronger LDF. Okay? Now, as far as how these influence properties, we talked about a couple of different properties. First off, state of matter. With those solids being the closest particles together, solids have to have the strongest IMF. Gases then would have to have the weakest IMF because there's a lot of space and movement between those particles. We talked about boiling point and melting point. And that's about the energy required to change the state of matter of those things. So if you have a high boiling point or a high melting point, that means that we had to have a strong IMF because it took a lot of energy to weaken those forces and change the state of matter. If something has a low boiling point or a low melting point, it's going to have a weak IMF because it doesn't take as much energy to weaken those forces between the particles and separate the particles into a different state of matter. The other thing we talked about was vapor pressure. And vapor pressure, again, is at the surface of a liquid, those particles, the liquid particles, escaping into a gas form. We all know that if we leave a bottle of water out on the counter over a couple of days, the amount of water that's in that container is going to start going down because it's going to start evaporating. We don't have to do anything to it, it's just going to start evaporating. And as those gas particles start to evaporate, they hit the sides of the container, exerting that vapor pressure. So the more particles there are means that we have more vapor pressure. And the reason why we have more vapor pressure is because we had actually a really weak IMF. And the IMF couldn't hold those other molecules in the liquid state of matter as easily, and it lets it escape into gas form. If we have few particles that are actually hitting the sides of the container, that means that we're going to have a low vapor pressure, And we have a low vapor pressure because we have a really strong IMF holding all of those particles together in that liquid state of matter. So I hope this helps, just kind of putting everything all together here. And if you have any questions, just please reach out and let me know. Thanks.